Okay, so let's start with a new topic, new and the last. We don't have much time left. So this is related to solar cells. And all right, so the first thing is how much of solar radiation is really available. When we are talking about solar cell as a device for harnessing solar energy and converting it into electricity, the first issue is how much of power is really available, right? So here are some numbers. So this is the outer surface of the Earth's atmosphere, outside, right? There are some applications, especially satellites and other space applications, where this number is of interest, 1366 watts per square meter. On the surface of the Earth, right, as the solar radiation passes through, it gets absorbed by various gases, water vapor, carbon dioxide, and other things that are there. So full amount of solar radiation is not able to reach. Only about 1000 watt per meter square reaches the Earth's surface here. And so this really shows you the spectrum here. So if you look at the yellow one, the yellow graph is the sunlight at the top of the atmosphere. And it really follows the black curve. It shows a black body radiation. Those of you who are familiar with black body radiation, you might have read earlier. A black body radiation depends on what temperature the black body is. And so this follows roughly that particular plot here. A black body at a temperature of 5000 degrees Celsius here. The red one is what you see reaches the Earth's surface here, the red one here, right? And there are, you can see here, absorption bands due to oxygen and water vapor and carbon dioxide and things like that here. The red one is at sea level here. But then, Earth is not flat, it's not the same. So different amounts of radiation reach the Earth at different latitude level here. And so for the sake of characterization, so there is a concept known as AM, air mass. So air mass is the amount of atmosphere or the amount of air mass that the radiation has to go through to reach your solar cell. So at the top of the Earth's surface, we call it air mass 0. It doesn't go, it's at the top of the Earth's surface, so it doesn't have to go through any of the air mass. If it goes vertically through the atmosphere like this and reaches the Earth's surface, we call it AM 1.0. But if it comes at an angle at most places, or depending on the time of the day, this may be more typical that the rays from the sun are coming at an angle, and then it goes through more of the air mass. And so, for example, if it comes at an angle as shown here, 48.2, we call it air mass 1.5. If it comes at a greater angle, we call it, there's a greater amount of air mass that it goes through, we call it air mass 2. So there are different amounts of radiation that reaches the Earth's surface or on top of the solar cell, depending on how much of air mass it goes through. So when you're characterizing a solar cell, in order for standardization to occur, so people normally quote that they're talking about the characterized solar cell under air mass 1.5. So most solar cell data and all that people quote is, they assume that solar radiation, which is AM 1.5, is falling on my solar surface here. And then they talk about what is the efficiency, how much power and all that is being generated via AM 1.5. So note that, as you can see here, depending on the time of the day and different latitude levels and different seasons, the air mass that the radiation will go through will vary. Okay, so this is AM 1.5 is just a standard that is there here. And air mass 0 is 1367, air mass 1 is 925. You can see the results of absorption. Air mass 1.5 is 844 watts per meter squared, so it's a slightly odd number. So normally when people characterize their solar cell, they assume an AM 1.5 radiation, but with they change this to 1000 watt per meter square. Although this is the amount of radiation that falls on the Earth's surface, AM 1.5, but this is a slightly odd number, 844, so they characterize it under 1000 watt per meter square, which translates into 100 milliwatt per centimeter square. So if you want to keep a number in your mind, right? I mean, if you're talking about how much energy can we get from the sun and all that, so the number that you need to keep in mind as a reference number is, there is 100 milliwatt per centimeter square that is falling on the surface of the earth, as an average number. Of course, as I'm repeating again, it varies, right? So 100 milliwatt per centimeter square, that's the number that you need to keep in mind, okay? Or 1000 watt per meter square. Now this radiation, 100 milliwatt per centimeter square that falls, is of course distributed. It has a spectrum, right? And this is the spectrum that you see here, right? A spectrum that you see. So it's plotted against wavelength in nanometers. So all this graph that you see, I'll share this graph, the data in an Excel file. So note on the y-axis is how much of milliwatt, of course per unit area, per nanometer, right? That's the spectrum. In 1 nanometer around this particular thing, how much of radiation is there. So it is all distributed, as you can see here. Now you can do a further analysis of this particular radiation. So these are measured data actually falling on the Earth's surface. So if you do an analysis, you find infrared is a region which is greater than about 700 nanometer. All right, somewhere here. This is 500, this somewhere around this, 700 nanometer. So all radiation greater than 700 nanometer will be, let's say, classified in infrared. Out of 100 milliwatt, 55 milliwatts is in the infrared, in sun's radiation. 41.6 milliwatt is in visible region, 0.4 to 0.7 micron. That's a visible region here. And UV is a small part, 3.34 milliwatt here. So that's the distribution of solar radiation here, 55, 41.6 and 3.34. So all that you need to do is, how do I calculate 0.7? So you go to a point, once you know the spectrum, you go to a 0.7, wherever 0.7 is. This is not likely to be 0.7, so this is maybe somewhere here. You go here and you integrate everything, here. Integrate everything and you'll get 55 milliwatts here. 0.4 to 0.7, you go somewhere here, 400, and you integrate here. You get this number 41.6 here, right? So this is what amount of energy that lies in different bands here. Now this is interesting because if you look at this number, infrared, right, 55 milliwatt here, it raises the possibility that you can make a solar cell, let's say, which absorbs only in the infrared. Suppose only in the infrared and allows all the visible light to pass through. Suppose you could do that by some means, right? So then it raises the possibility that you can have a reasonable transparent solar cell. A solar cell which is, let's say, made on glass and using a material which allows the visible light to go through, but absorbs only in 55 in this particular region and generates reasonable, maybe generates 10 milliwatt or something like that, let's say, right, per centimeter square, right? So it raises the possibility of transparent solar cell. Why is this important? Because you could take in the building especially, you could take windows and skylights and things like that, and you can cover it with these transparent solar cells, so they will allow sunlight to come through also, and at the same time they will convert generate electricity also, right? So it raises an interesting possibility when you look at these numbers that you can have a reasonable solar cell which absorbs only in the infrared region here. All right, so this is just the background to having an idea about what is this radiation that is falling on the Earth's surface. So the things to keep in mind is 100 milliwatt per centimeter square. That's the number always to keep in your mind. That's the amount of power that is falling. Out of that 100 milliwatt per centimeter square, roughly half is in infrared and half is in visible, right? Half and half. That is the idea. All right, so how do we convert this solar energy, these photons that are falling, into this thing here, into electricity? So the basic idea behind this is, as you know, So the photons are supposed to get absorbed in the semiconductor that you're using, creating electron hole pairs. And then you need some means of separating the electron hole pairs, because once the electron hole pairs are generated, you know that they can recombine also. And if they recombine, then recombination, as you know, what really happens in, let's say in silicon, we have discussed this in detail, recombination occurs through defects. So if you have an electron and you have a hole, the electron falls into a defect, this falls into this one here. And eventually, where is the energy gone? Energy of the photon, it goes to the lattice in the form of vibrations and heat. So it's all lost as heat, right? You don't get electricity. So you don't want this to recombine. So you want this, once the photon is generated, you want the holes to go towards the anode and this to go towards the cathode. You want to somehow separate them. So that's, you want this to go here, you want this to go here. And then if you connect this thing here, then of course the current will flow and will generate electricity here. So the key point is, in this, what you see here is at least two things to create a solar cell. You need to absorb the photons, right? So you need to have the right absorption characteristics, right band gap and things like that to absorb that particular photon, right? And so that's a challenge, because note that the photons are available in visible and as well as infrared. So how do you absorb all the, to convert the highest efficiency solar cell, you want to absorb all the photons, right? You don't want to ignore any of those photons. So the first challenge is absorbing them. How do you absorb all the photons? Because that's one. The second challenge is, once the photon is absorbed, you need to separate them. If you don't separate them, then they're going to recombine. Then they're going to recombine and they will be lost. So the other challenge is separation of electrons and holes, right? So these are two challenges that you're seeing here. All right, let's look at absorption in a little bit detail here. So how do people characterize absorption? So let's say you have a piece of semiconductor, the incident light is I0, and it goes through a thickness D, so light is going, right? And some light, let's say, comes out at the other end. Especially if the material is not very thick, some light will come out. And so we model it using this equation, that as the light intensity goes in, it exponentially decays, I0 exponent minus alpha x, and alpha is called the absorption coefficient. So that's what happens, if that's what happens to light as it goes through. A very simple model of light intensity, that it decreases exponentially with absorption coefficient alpha. Units are 1/centimeter. So for 90% absorption, because it's exponential, you can see here, you require a thickness which is D equal to 2.3 by alpha, right? So this is an important number here. How thick a semiconductor do I need if I want to absorb most of it, 90% of it? Well, it's related to alpha. What is the absorption coefficient? So it's a key parameter. And note that absorption coefficient, as you will just see, is a function of lambda. Different photons have different absorption coefficient. Okay, so I'll show you some data here. And one of the things that you know is that if I have a semiconductor like this and its band gap is Eg, then I'm only going to absorb E greater than Eg, right? Because anything less than that, I don't have enough energy to promote electrons to the conduction band, and so will not get absorbed. So there is a cutoff wavelength. And that cutoff wavelength for silicon you can easily calculate by putting band gap here. You put here 1.12 EV here, and from there you can calculate what is the cutoff wavelength, which is 1.1 micron. So silicon is not going to absorb anything less than about 1100 nanometer, right? And it will absorb everything above it. It's capable of absorbing. Whether it will actually absorb or not depends on, have you provided enough thickness of the amount of silicon that is there here to absorb, right? So this is the cutoff wavelength for silicon to keep in mind, 1.1 micron or 1100 nanometer here. Let me show you the real absorption coefficient of silicon. This is how it goes, alpha, right? So alpha is a key parameter. How does silicon absorb a photon? Well, it's characterized by alpha. How much of alpha is there? So note that at 1100, at around this 1100 nanometer, alpha goes to 0. because that's the wavelength set by the band gap. After that, note that alpha is not that, the characteristics is not like below, a simplistic understanding of alpha would have been, let's say, with energy of the photon. Let's say this is Eg, that's 0, then goes up and like this. It's not simplistic like this here. That above Eg, it will absorb all the photons, and above Eg, all photons are identical, right? In terms of, no. Note that the absorption coefficient is varying with the wavelength here, right? So now the issue is, let's say you want silicon to absorb, you want to create a silicon layer, right? You want to create a silicon layer to absorb all the photons that it is capable of. If you want to make a silicon layer which is capable of absorbing all the photons that it is capable of, how thick should the silicon be? What do you think? All the photons that it is capable of, how thick should the silicon be? Note that, what did we say? D equal to 2.3 by lambda, right? So how thick do you think the silicon should be? If you want it to absorb everything from let's say 1000 onwards. So 1000 is, let's say, I don't know, I'm not drawing accurately, let's say 10 to the power 2. So then D required is 2.3 by 10 to the power 2. So now what does this become? This is in centimeters. So this becomes 2.3 into 10 power minus 2 centimeter. And this becomes then 2.3 10 power minus 2 into 10 power 4. Let's convert this into microns. So this becomes 20, huge, 2300 micron, right? What is the silicon wafer thickness itself? You can only make maybe 300 micron, 400 micron. That's a typical silicon wafer thickness. So even though silicon is theoretically possible to absorb everything from 1100 nanometer, but you need very thick silicon there, because the absorption coefficient is very, very low. So realistically, if I say if I say the thickness of silicon that I'm going to use is, let's say, 200 micron or 250 micron. Well, if it's 250 micron, how much of photons will it be able to absorb? Well, you have alpha, which is given over here, right? And you have 250 micron. You can determine what fraction of the photons are going to be absorbed. So you see there's a problem with silicon, that yes, for longer wavelengths, the absorption coefficient is pretty low. Even here, suppose I go, let's say, is coming to be 23 into 230, sorry, you're right, 230 micron, right? 230 micron. So even it's okay, so even if I use 250 micron, 250 micron, I will be able to get, let's say, 90%. Okay, 250 micron, I'll be able to get 90% here, but it's a very, very thick silicon. It's an extremely thick silicon, and some of these will be missing. Some of these will be missing here. So the issue before us is, the point that I wanted to make was that, if I have to use a very thick silicon to absorb. Very thick silicon to absorb the radiation that is falling, and the reason being is the low values of alpha that you see here. The higher values of alpha, if I have 10 to the power 4, they'll get absorbed very quickly. The lower ones will take they'll have to travel longer distance, and 10 power 2 and all that will travel even longer distance before they get absorbed here, right? So this is something that you have to keep in mind. The alpha goes like this here, and I need at least 250 or so micron to absorb, and this is the the data here that is here. Okay. Now, because of this cutoff here, What I'm missing in silicon is that 38% of the photons are not absorbed by silicon, cannot be absorbed by silicon. Everything which is greater than 1100 nanometer will not be absorbed by silicon. So all that 1100 I can put here, something like that, 1100, and all that radiation will not get absorbed. And how much is that? Is 38%. So first of all, if you're making a solar cell using silicon, 38% or let's say 40% is already gone. 40% it cannot absorb. So silicon efficiency can never be greater than 60%. 40% is already gone. You just cannot absorb. Silicon is not capable of absorbing. Okay, so that's just because of his energy gap here. All right. Now the other part is so we are talking about, let's say, silicon as a material, silicon as a semiconductor. Fine, so it can absorb, let's say, 62%. Now, what I want to show you is that yes, you can absorb 62%, but your efficiency of a solar cell is going to be considerably lower than 62%. Right? This thing. So first loss is what you see. Let me put it here. So first loss is out of I can only get 62%. 62% of photons are absorbed. Of photons, I would say, can be absorbed. Can be absorbed. But note that what would happen in practical, let's say you have piece of silicon, and you have electrodes and all that. And there, when the light comes in, two things will happen. This is air, and this is silicon, and there is reflection, so light starts to get reflected. Not everything that falls gets into the material here. So there is a reflection here. So there are reflection losses. So a big problem is, how do I minimize the reflection losses? So you want everything that is falling in, you want it to get into the silicon, right? So reflection losses have to be minimized. So you have to do something to the surface of the silicon. And they have something called, we'll not go into the details, we don't have time. They have something called AR, anti-reflection coating. So the whole idea is to minimize. These are materials with proper dielectric constants and all that to minimize this thing here, okay? To minimize the reflection losses. So you need that. Then a major problem with this is, look at, so silicon is 62% of the photons. So these are all photons with energy greater than E greater than 1.12 eV, right? So now you see what happens here. So you have, let's say you have a photon of 1.5 eV. So 1.5 eV, this band gap is 1.12, right? So a electron comes in and you absorb a 1.5 photon, let's say it goes like this here, right? 1.5 photon. This is EC and EV. So the electron, or let's say, which is generated is a higher energy electron, right? What happens to this electron? This electron, which is above the conduction band, let's say, what will happen is, it will immediately lose that extra over 1.12, loses its energy and come back to the bottom of the conduction band. This process is very, very fast. Any, electrons, conduction band and all that, if you somehow promote an electron higher up in the conduction band, very, very quickly it will fast. In almost like maybe picosecond scale. It will just fall to the bottom of the conduction band. It just loses energy. Before you can even separate them and move it to the different electrodes. So all this energy, you absorbed 1.5, so almost like 0.4 eV, where did it go? Just went as heat. Again, you may absorb a photon of 1.7 EV. Where does 0.7 EV go? Heat. Why? Because the electron just falls into the conduction band. All that energy is gone. So yes, you are absorbing everything larger than 1.12, but all that extra energy is not getting converted. You are only able to, finally what you are able to get is an electron here and a hole here. Finally, the electron will be at the bottom of the conduction band and hole will be at the top of the valence band. So effective energy that you have generated through photon is only 1.12 eV. You absorbed 1.5 eV, but effective energy that you are left with in your system is only electron and hole separated by 1.12 eV. So there is a loss that is occurring because of this. Right? So this will also bring down the efficiency drastically, because 1.5, 1.4, 1.3, all those photons that you're absorbing, you're left with only 1.12. Okay. Now the issue is, this is the internal energy of the what you are left with. So you can take as a reference 1.5 eV is what you absorb, but you're left with 1.12 eV. But how much energy is the solar cell able to deliver to a load? How much is it able to? So it's the voltage that is able to develop across the load. Voltage is related to energy. So from 1.12, the amount of voltage that the solar cell is, energy and voltage are related together. So the amount of energy that the voltage is able to generate in the external circuit is only about 0.7. Because as you will see, it's basically a diode. So you're only left with 0.7. So what is happening? You're absorbing 1.5. इसको बाद में कर दें? ठीक। So you're absorbing 1.5 and what are you left with? 0.7. You're absorbing 1.7 and what are you left with? 0.7. Because the solar cell, when it's driving a load and all that, it's only able to generate 0.7 or 0.6 or something like that. So all that photon energy is all getting wasted. Right? So, and because of that, what you are saying is, yes, 62% is theoretically what my silicon is able to absorb, but eventually you will see that what you are able to get is only 25%. The best silicon cells are around this. Best silicon cells are around this, 25%. So there are all these losses that are there that you see here. 62%, first loss is because of the band gap. It can only harness 62% of the energy. After that, I'm pointing out that out of the 62% also is losing almost like half. Half of the energy is being lost. Right? And you're left with 62, so you're left with almost half, which is like 31% or something like 25%. Right? So all that is getting lost here. Okay. So now if you're wondering, the next question for us is, if you're wondering what is this solar cell? I'm saying right now I've only talked about that you have a piece of semiconductor which absorbs. Right? But now note that, fine, absorption is one thing. The other thing that you need to do is, you need to separate the electron and the hole. You need to separate them out. They need to flow in opposite directions. Right? And for that, for separating them is what we are using as a p-n junction. For separating the electrons and holes, we are using a p-n junction. And once we use a p-n junction, then you will see it can only result in a voltage of around 0.7 or so at the most. Right? So the desire to separate electron hole pairs leads to a p-n junction, leads to 0.7 volt in the external circuit. So all that extra photon energy, all you're left with is 0.7 volt here. All right, so let's come to then p-n junction. There is a lab exam that I have to leave early, so we'll stop at 1 today. All right, so, okay. Okay, so so we've been talking about alpha intensities and all that. If there is a number that you need to keep in mind, because when you talk about generation, when you look at semiconductors and you look at continuity equation, there is a generation term G. So how much of, if you want to keep some number in mind, how much of the generation rate occurs as a result of solar? So what I've done is some simple calculation for by taking the same model, how the light intensity goes. So note that in a small area like this, the amount of light intensity which gets absorbed is basically delta Ix. So this is given here. And converting it into a generation rate. So this is alpha times Ix, and dividing by energy will give you a generation rate. I would suggest that all of you do this calculation yourself. So for example, for lambda equal to 550 nanometer, I have a value of alpha, I have a value of h mu, and I have the initial intensity 100 milliwatt per centimeter squared. So if I put in all these numbers, I get 10 to the power 21 per centimeter cube per second. So what is the generation rate as a result of solar radiation falling into my solar cell? This is a number that you can keep in mind. Of course, it would vary as you change the lambda. As you change the lambda, h mu changes, alpha changes, all those things will change. But this is the peak. This is where the peak of the radiation occurs, 550 nanometer. So this is the amount of generation that occurs here, 10 power 21 per centimeter cube per second. So, right, so as a reference number to keep in mind. Okay, so solar cell is a diode, right? And let me skip this for a moment. So you look at this PN junction, right? So most solar cells most of them are PN junctions. There are some which are not PN junctions, but you know, we'll see that later on. So I've shown you a PN junction here, right? And note that the junction depletion width that you're familiar with is how much? A number? What number would you put? Depletion width? It is some number. I mean, is it 1 nanometer? Is it 100 micron? What is it? What number would you put? Depletion width. Let's say you take a PN junction, you know, average dopings at zero bias equilibrium. How much is the depletion width? Some number you should give. I mean, say somebody gives 1 nanometer, right? You'll say, no, it's ridiculous. Correct? Totally wrong. If somebody tells you 10 micron, totally wrong. Right? 10 micron is not the depletion width. I mean, if I take, let's say, 10 per 16 doping here, 10 per 16 doping here, and all that, I will not get 10 micron. I will not get 1 nanometer. What will I get? Huh? Point? Okay, so what she's saying is maybe 500 nanometer, right? 500 nanometer, 200 nanometer, something of that sort. Okay, so let's take the order of maybe say 100 nanometer order. Okay, so maybe 200, 300, something like that, 100 nanometer. What is the thickness that is required to absorb the radiation we just said? 2.3 by lambda. So this was coming out to be hundreds of microns, right? 100, 200 micron. So where is most of the radiation absorbed? This is a big misconception that exists among students, that the photons that are coming in, they get absorbed in the depletion region, and the electric field in the depletion region separates them out. Right? But look at the depletion region thickness is 100 nanometer. The silicon where thickness where what you need for absorbing is hundreds of microns. So where are most of the photons absorbing? Where are they getting absorbed? All here, here and here, all outside. The amount of photons that get absorbed in the depletion region is negligible. The amount of photons that get absorbed in the depletion region is negligible for solar cell. It's all outside the depletion region. If nothing is getting absorbed in the depletion region, the electric field is not playing any role of separating electron hole pairs. That's an important point to keep in mind. That's why we did the calculation. How much of thickness do I need for absorbing the solar radiation? We need hundreds of microns. Depletion region is only very, very narrow. right? So what is the role of the depletion region? Why am I using depletion region? If nothing is getting absorbed in the depletion region, and electric field is not, if nothing is getting absorbed, so electric field is not involved in removing electron hole pairs and all that, what is it that's doing here? Okay, so that's the question that we would like to look at it in a little bit more detail here. Now, you know, if you go back and look at the derivation of p-n junction, most of you are familiar with this part here. J equal to Q dp LP Ni square and all that, you know, that is there here. Now, all this derivation that is done is that there is no optical generation rate, right? So all we need to do is we need to go back and look into this equation. Let's say continuity equation, del P by del T is 1 over del JP by del X plus G minus R, you know, like that. So all you need to do is redo the derivation of p-n junction, but now you have a G here, generation rate, and G is what? Optical generation rate. Redo the whole derivation step by step, but add in the continuity equation, add a GOP term, that there is an optical generation, right? So I'm not going to go through that. If you do that, then this is the equation that you get here. I'm just going to give you the final equation. This is what you end up with. So you have the whole equation as it is, but you get this extra term here, Q GOP LP plus Ln, right? So I mean, what is this term really telling you? Q GOP LP plus Ln. As I said, this is under what? By assuming that there is an optical generation rate GOP throughout, uniform. It's not going to be uniform in practice, because photons, if they are coming in from here, more photons may get absorbed here, less here, and all that, you know, is exponentially decreasing light intensity, right? So it's not going to be uniform. But let's say, as a first order model, assume that there's a uniform optical generation rate. Then this is what you end up getting, Q GOP LP plus Ln. What is this telling you is the following. If you look at this particular term, it's telling you this is the forward bias current, right? Normal forward bias current that you have. What it is telling you is that within a diffusion length of, let's say if you look at LP here. So what, if you look at this, what it's saying is Q GOP, there is generation occurring all over. But generation which is occurring within the diffusion length of the junction, GOP times LP, and similarly GOP times Ln, within a diffusion length of junction. So what is really happening is, if you're creating electron hole pairs, note that the difficulty is the hole here. The electron is already in a majority n-type layer here. So the difficulty is the problem of hole, because hole is, what is going to happen? The hole is there in the midst of all the electrons, large number of electrons. If you look at this electron hole pair in this n region, the hole is in the midst of all these electrons. So the hole has to survive. And where does it have to go? The hole has to go towards the anode. So the hole has to move towards like this, go in that particular direction. The hole has to go here. Once it comes here, note what is the direction of the electric field? Like this. Once it comes here, then the electric field will sweep it here. And then it comes into a P region and all that is collected. So for a hole, what it has to do is it has to make a journey to the edge of the depletion region. Then the field will take it and bring it into this region here. Right? So now a hole, but what is the danger for it? The danger is it can recombine. So what is happening is a hole within the diffusion length. That's the meaning of, within the diffusion length. That's the meaning of diffusion length. Is the average length a hole travels before it recombines. So a hole within the diffusion length of p-n junction is able to get collected. Any hole which lies here, let's say hole lies here, what is it likely to happen to it? Recombine. It's not going to make it to the p-n junction edge. Is going to recombine. Any hole which is here will also get recombined here. So what you are going to harness is only within the diffusion length. right? So now if you look at diffusion length is square root d times tau. So you want diffusion length to be very large, right? You want diffusion length to be very, very large because you want to collect everything, right? So diffusion length has to be very large, which means d is a constant. It doesn't change much. So you want lifetime to be very, very high lifetime. And high lifetime actually means very few impurities. We have discussed it's all the defects and impurities. So you want a very pure material, very, very pure material with large diffusion length, right? So that has to happen. So that's the reason why solar cells are all made on very, very high quality silicon. And that makes the solar cell also very expensive, because if it's a high quality silicon with very few defects and all that, it becomes an expensive thing. The other thing that you may be wondering here, why can't the hole just go here? Sorry, electron hole that is there here, it can also go here. There is no field at this particular point, right? It's a neutral region. The hole can diffuse here also, and it can recombine also. You want the hole to go here. So there is a hole which is created. So note that what needs to happen is there is a hole which is created, hole electron pair. You want the hole to move here. You don't want it to go here. How do you prevent holes from going? Because any hole which goes right is lost. Eventually it all recombines here, or it recombines near the contact, is gone. So you want to prevent holes from going right. You want the holes to go towards the left. Right? How do you prevent the holes from going right? Do you know of any way you can prevent the holes? It's outside the depletion region, right? So you have to prevent them. So one way of doing this is you create what is called a back surface field. Back surface field. So suppose I could, make a band diagram here. Band diagram like this here. Suppose I have a band diagram, EV goes like this. Sorry, let me draw. So say here. So this is EC and this is EV. So you're able to create in this region something like this here. I'm sort of exaggerated here, Elijah. It should be because it's an N region here. So what do you see here? Here is N plus, or here is a doping is becoming less here, right? This is the Fermi energies, the separation is higher and all that. Why am I saying it? Because if you have a hole and you have a band diagram like this, somewhere hole here and a band diagram like this, so note that hole will have difficulty, hole has a difficulty going down in energy. So you are almost like creating a barrier, right? So you need to do something here in this region so that you get a band diagram like this, right? Band diagram like this. So hole which exists here cannot go on towards the contact and recombine. You have to prevent holes from going to the back. And then why do holes want to come here? Because you have created a depletion edges there and all that, so holes may want to come here and diffuse and get collected. This is like a sink here, right? So you have to do these things here in order to prevent the hole from going towards the opposite side. You want the holes to go towards the left here, right? But you only can collect everything within the diffusion length holes. All right, so that you have to note that if you are absorbing, we said the absorption length is of the order of 100 micron. So you need diffusion length of the order of D also. Diffusion length has to be of that particular order to absorb everything. So you can do the calculation L equal to D, so you can do square root D tau, put in values here, how much of lifetime do I need and all that, okay? All right, so those are what do I have to do in order to collect. So this is what this particular equation is telling you. So you can intuitively understand I mean, it comes from the derivation, but you can understand what it means and why it means like this, Q GOP LP times Ln here. Now, if you look at this equation here, all right, so let's look at this equation. This equation that you see here, you represent by a diode, right? It's a normal diode equation. How do you represent this? Does it make sense that I've represented it by a current source? Right? Why is it a current source? So now we are talking about a solar cell. So according to this, solar cell is a diode. The first term is a diode. But along with the diode, there is this term here. How do I represent this term? If you see Q, GOP, LP and Ln, is there any voltage dependent term here? It is current, you're right. It is current, but it's current which is independent of voltage. So how do you represent it in the form of a circuit? A current source. A current source. And what is this current source due to? Its value you know. What is this current source due to? It's because of light. If you don't have light, this GOP term will go to 0 and this term will not be there. So that's where you can see that solar cell is a diode in parallel with a current source. And the value of the current source is, we call it IL, or photo-generated current, IPH. Is a photo-generated current. You can call it JPH. If you multiply it by area, you will get IPH. So it's a photo-generated current. So how much is this photo-generated current? Average optical generation rate multiplied by LP plus Ln. So there is a certain amount of photo-generated current. So this is what a solar cell looks like. A diode and an IPH. Right? So it's basically a PN junction with a light generated current source. Okay? And the origin, why we are representing it by IPH, is this equation here. When we do the derivation of a solar cell, this comes out like this here. And this term is a current source here. So that's why we represent it in this. It's just a mapping of this equation into a circuit element. All right? Now, let me see how much time today I have here. Okay. Now, the thing is, what I want to address is PN junction, or maybe we'll do that in the next lecture. Is PN junction necessary to harness energy? Or I can do it in other ways. Why can't I? So the question that I'm raising is, why can't I simply take an N-type semiconductor, and convert a load? So normally what is happening is you're taking a PN junction and you want to get light out. I mean, you want energy out, you put a load here, R. Right? And it will generate, it will pass current through the load here. But why can't I take simply an N-type semiconductor and connect a load here? Will it not work? And if it will not work, why will a simple N-type semiconductor not work? And what is it that I really want to make a solar cell here? What is really necessary? Is PN junction really necessary? Or is something else which is necessary? And PN junction is one way of implementing that necessary condition. Right? So intuitively we know that you have to separate things out, electron hole pairs. But can it not separate? Can a N-type semiconductor not separate? Is that not possible at all? So what we want to do is the following. We want to solve this particular problem here to show you. Okay, so it's a lot of things are here, but what we are saying is this is an N-type semiconductor, and we'll go through details of calculation here, and it will illustrate to you lots of things. So it's an N-type semiconductor with a doping of 10^17. Okay? There are two ideal contacts. Left hand side, right hand side, ideal contact. Now note that ideal contact is what? One of the definitions of ideal contact is like it has no resistance, 0. The other one is an ideal contact is always in equilibrium, which means that there cannot be an excess electron or hole density. That's an ideal contact, which means anything which reaches that ideal contact is immediately collected. It's like an ideal sink. It's an ideal source as well as ideal sink. Right? So in that sense, there is no excess electron and hole density at the contact. Delta N equal to 0, delta P equal to 0 at both sides here. Right? Now the other thing that we are saying is, imagine that I'm going to generate just at x equal to 0 this generation rate. That there is a generation rate only at x equal to 0. It's like a delta function, right? Because note that generation at any other points, you can understand if you understand what is the impact of generation at one particular place. Then because the generation due to at other points is just a summation of generation effects of generation at one particular point. So to simplify, what we are going to see is this generation occurring only at x equal to 0, which means you are absorbing electron hole pairs, and this is the generation rate. And I've given you generation rate is 10 power 16 per centimeters cube. What happens in the device? So you're creating electron hole pairs, and note that this is at x equal to 0. So this is L by 3 located, and this is about L located here. It's asymmetric generation, just to keep it general. So what will happen to electron hole pairs once you generate electron hole pairs like this? Note that everything is getting collected here, right? So electron hole pairs will maybe go here and go here. What will happen to the current? So this is the problem that we are trying to understand. Simple n-type semiconductor. At one place you are generating electron hole pairs, and we are asking what happens to the currents and everything, what really happens. Okay. Now PN junction is a very special, PN junction is a special case where note that in PN junction what is happening? Also at one place maybe electron hole pairs are generated. They can go left, they can go right, except that the boundary condition is something else. If it goes here, there's something else which is happening here, right? So it's also of the same nature here. You're generating here, it can go left, it can go right, electron hole pairs can disperse, right? You create excess electron hole pairs at x equal to 0. What will happen? They're going to diffuse. They're going to go diffuse right and diffuse left. What happens exactly? Is there no current? And if there is no current, why there is no current? What is really going on here? Okay, so this is the problem that we will spend some time looking at, what is happening here, because that will give you insight into lots of other things. If generation occurs, there is going to be minority carrier current, there's going to be majority carrier current. Why is the net current? Is it equal to 0, or can I get a current? Do you think we will get a current? Huh? Okay, yeah, the other thing is if you do the calculation, I've taken here is 1 micron, the diffusion lengths and all that are much larger, right? So if an electron hole pair which is generated, it will be able to easily go here. So will there be current? If it were right in the middle, let's say, then it's a symmetric situation. You'll say same number of electrons are going, same number of holes are going here, maybe no current. But if it is like this, what is your intuition? Will there be current flow in a device like this? N-type semiconductor, shorted. I generate electron hole pairs at x equal to 0. Will a current flow or not? No current? Why not? Why will no current flow? Okay, to analyze this, where will you start? What is your starting point to analyze this? It's a very, very basic semiconductor problem. N-type semiconductor, generation at one particular place, ideal contacts and two ends, right? Now, how would you start with this? What is your starting point? Diffusion current, then what will you do? Yeah, okay, diffusion current. You'll say there is both JP and JN. So JP is minus Q dP. What do I do with this? Del P by del X. Why not drift? Q mu Pe. Huh? So note that no voltage applied. So you have Jp and Jn. This this could be a starting point. Currents, everybody knows this. Current expressions are this. So now what she's saying is E is 0. So I should use Jp equal to minus Q dp del P by del X and Jn equal to Q dn del N by del X. That's the first simplification that she's suggesting. Would you agree with this? Would you agree? Would you make that assumption? What you have is, would it not be true that you would have E dx is 0? X equal to, let's say, minus L by 3 to L. This is true, right? There is no argument about this. But from here, can you really say E is equal to 0? That electric field is 0. Electric field could be in a certain way so that when you take its integral, it turns out to be 0. Can somebody say, why is this, can this be true? Can this be true? What will you do next? Okay, suppose it is true that E is negligible. So this is Jp is minus Q dp del P by del X, Jn is Q dn del N by del X. What else do we know about this problem? So this is stemming from saying electric field is 0. What else can you say about this particular problem? We said, note that these region L equal to 1 micron and minus L by 3, these regions L, whatever L and L by 3 obviously, is much smaller than diffusion length. What is the implication of this? What does it mean if it's much less than diffusion length? Huh? Yes, excess carriers. Excess carriers are linear. Where does that come from? Where will it come from? This is fine. Let's say we agree with this. There's no problem. So what I'm trying to point out is this is true. Is this true or not? We're not sure. What I'm pointing out. But let's say for a moment we assume this. So this is true. Anywhere that I put blue tick, which means fine. We have no arguments about that. So how do we know that carrier density is linear? How do we tell that? Where do you go? So this came from from a calculation, right? Square root d tau and all that. So that's not a problem. How do you tell? Continuity equation. So right, so you go to continuity equation. So you go del P by del T minus del Jp by del X plus G minus R. Right. So now when you say L by 3 and L is much less than diffusion length and all that, LP and LN, what are you saying really? The length of the device is much smaller than the diffusion length. What are you really saying? First of all, G is 0. Note that G is only there where? Only here at this particular point. It's a delta function. Everywhere else G is 0. Correct? So I can put G equal to 0. G is 0. What else are you saying? You're right. You're saying if this is true, it implies R is also, you can say, negligible. Recombination you can ignore. And this also is 0. Why? Because we are talking about steady state. So what are you getting really? You are getting del Jp by del x is 0. So what you are getting is Jp x is constant. That's what you're getting, right? And similarly you're getting Gnx is maybe constant. Right? You're getting both, because I can apply this to same here, similar to, you get Gnx is a constant. So now Jpx is a constant and Gnx is a constant. Now if you say, note that if you say Jp is q dp del p by del x, and if you say this is a constant, then you will say P is linear. Right? So note that this is fine. Right? Jp and Jn are not changing with x. That we could say. But then if this is, then we say is linear. Right? If you assume linear. So now because of what has been said, E equal to 0, you assume it to be true. Then you are saying, I will assume it to be linear. I will assume it to be linear. So what does your problem really look like? Problem looks like this is x equal to 0. This is x equal to minus L by 3. And this is x equal to L. So you have n-type semiconductor, you've generated some excess carriers, right? So something like delta P0 would be there. How is it going to go? What is delta excess carrier density here? We've already said 0. What is excess carrier density here to the contact? 0. So how will the hole density go? Linear. This is how hole density will go. Because this thing here. How will the... So this is how delta P0 goes. How will delta N, how will it go? By the way, if you write delta P0, so what would be the current then? How will the current go? Jp. How are the holes diffusing? From delta P0, holes are diffusing like this. So what is the amount of current that you get? Current you will get like this, constant, equal to q dp delta P0 by L, diffusion current. And here you will get minus q dp delta P0 L by 3. That's how you get the current, Jpx. Right? Jp is q dp del p by del x. Okay, so far fine. This is okay. This is okay. Total current through the device should be constant. Total current through the device should be constant, right? J should be constant. J equal to Jn plus Jp equal to constant, correct? Whatever that current is steady state, same current will flow everywhere. So there must be Jn somewhere. This can't be the situation. Jn is also flowing. So what happens to Jn then? How do I calculate Jn? So this is Jp. Then how do I calculate Jn? Should I say delta Nx equal to delta Px? Should I say that? Yes or no? Delta Nx equal to delta Px. Is the region neutral or not? N-type region is neutral, and then you created one electron hole pair that's neutral. So I should say delta N equal to delta P. So then you will be able to draw delta n0 also. And then you will be able to, so same thing, you will be able to get, if this is true, if you agree with this, then you will be able to get delta n. And then you'll be able to get Jn. And then you add up Jn and Jp and see. So do that, we'll stop here, do that, and what you find is that Jn plus Jp is not a constant. Right? Jn plus Jp will not come out to be constant. Then what do we do? Where do we go from here? What is wrong then? What did we miss? Where are the errors? Where are the errors in this? In this whole analysis now? So assuming that currents are diffusive, right? You end up with, you just do the calculation for Jn also, draw it together, add up Jp plus Jn, you will find it's not a constant. So somewhere something is wrong. Current has to be constant. Whatever the value, 0, non-zero, whatever, it has to be constant. It's not coming out to be constant, which means some error has been made. Drift component of the? So, which means then there is an electric field, right? So now, so the issue is then, how do we take into account the electric field then? How do we calculate the electric field in that region here? So that's where we'll start, okay? So let's stop here.